Okay, so hello and welcome to our C11 Hydrology Prelims Part 2. Okay, so uh, yan. So, in Part 1 na-discuss natin, or recall lang tayo, in Part 1 na-discuss natin yung precipitation, yung pag-estimate ng missing data, and then pag-convert ng point rainfall data into aerial data using station average, isohyoidal, and TSN polygon methods. So, the same reference. So, for this one, medyo mas mahaba to. Ang tatalakayin natin ay yung hydrographs, baseflow separation, master-depletion curve method, baseflow and direct runoff, separation of losses using index methods, and then separation of losses using infiltration capacity curves. So, nag-start na tayo sa pag-compute ng, so ito may epekto sa pag-compute ng runoff or kung magbabaha ba doon sa isang lugar. Okay, kasi syempre pag nag-infiltrate yung water and na-saturate yung water, soil, pag na-saturate, so ang tendency magkakaroon na ng runoff. Pag matindi ang ulan, like dito sa Philippines, so kaka-relate tayo dyan. So, ano ba yung hydrograph? So, one purpose of hydrograph analysis is to analyze measured rainfall and runoff data to obtain an estimate of the transfer function. Once the transfer function has been developed or identified, it can be used with design storms and measured rainfall hydrographs to compute or synthesize the runoff that would be expected. So, the resulting runoff hydrograph could then be used for design purposes. Yan. So, yung runoff or yung discharge, yung water na ma-accumulate, so yun yung ginagamit sa pag-design ng mga drainage systems. Sa pag-design ng roof, ng plumbing, ng sanitary, ng sewerage, and the likes. So yun yung purpose ng hydrographs. So ano ba yung hydrograph? Ano ba itsura niyan? Yan. So yan yung hydrograph, guys. So ito. Yan. Actually, iba-iba ang may mga iba't ibang model kasi ang hydrograph. Pero, ito yung raw hydrograph. Okay, so, basically, it is the rainfall intensity versus time or with respect to time. So, sabihin ng intensity, yung lakas ng ulan or yung dami ng ulan. So, ano yan? Normally, the rainfall intensity is measured in inches per hour. And then, ayan yung time sa kabila. So, yan. So, doon sa isang rain gauge, after some time, or bawa, 30 minutes, ganito kataas yung na-accumulate na rainfall. Or ito yung depth ng rainfall. And then, after 30 minutes ulit, ganito na siya. Then, 30 minutes ulit, and then 30 minutes ulit. Ibig sabihin, palakas yung ulan. Then, syempre, hihina din yung ulan. So, titigil din yung ulan eventually. Bawa, wala na yung bagyo, or wala na yung nagkakos nung storm or ng rainfall, so syempre magsasubside or hihina rin yung ulan. So bababa yan eventually. Yan, parang ganyan. Nasa mawala. So ang tawag dito ay hydrograph. Kaya, for example, sa isang storm event, like, halimbawa, may bagyo, so pwedeng tayong magkaroon ng hydrograph or pwede natin siyang gawa ng hydrograph. Okay? So madali lang naman 'yun. So, ang Pag-asa, marami silang hydrographs sa iba't ibang lugar, kalat-kalat yan. Kaya nalalaman nila yung dami nung ulan na bumabagsak sa isang lugar dahil doon sa bagyo. For example, doon sa bagyong Ulysses or sa bagyong, di ba, ang dami niyang ulan na binagsak na same daw nung sa Ondoy. So, yun. Then, also, nakakapag-forecast din sila gamit yung mga, na yan, yung mga gauges na yan. So, yun yan, it is important. And, syempre, aside from meteorological purposes or sa pag ng weather, pag forecast or weather forecasting, sa design or sa mitigation ng flood. So, importante din yung hydrographs. So, ang titignan mo kasi dito, yung tagal, gaano ba katagal yung ulan, and then ano yung peak. So, importante yung peak gaano karami yung iuulan or yung ibabagsak niya. Ibig sabihin yung volume. ng water. So, that's very important. Yan. So, transfer function ay ginagawang unit hydrograph. Sabihin, kino-convert kasi merong process ng converting. Yung unit hydrograph nagiging 1 inch or tina-transfer or kino-convert into 1 unit. 1 inch lang yung precipitation. So, pag-aaralan natin yan sa, I think, sa medyo finals na. Yung unit hydrograph. And, okay, so yung output function ay pinagsamang runoff and baseflow. Yung baseflow, dyan nag-occur, or ito yung, dito nangyayari yung mga losses or yung infiltration sa baseflow. Yan, so, ito ay isang example ng hydrograph sa isang specific na storm event. Yan, so, yan, may nakalagay na oras dyan. Ito, yan, may date pa siya. Yan, may oras. Baseflow separation. So, the baseflow is the water discharged from an extensive groundwater aquifer. So, the term hydrograph separation refers to the process of separating the time distribution of baseflow from the total runoff hydrograph. So, pinaghihiwalay yung runoff or yung pagbaha at saka yung baseflow o yung mga napupunta sa lupa. The direct runoff hydrograph is the discharge between the total runoff hydrograph and the baseflow function. By far, the easiest method to use is the constant discharge method. Simply stated, the line separating baseflow and the direct runoff begins at the point of the lowest discharge rate at the start of flood runoff and extend at a constant discharge rate until it intersects the recession limb of the hydrograph. So, tingnan natin. Yan. So, there are 3 methods ng baseflow separation. So, bakit ba kailangan yung baseflow separation? Siyempre, sineseparate niya yung runoff. Bakit kailangan mo yung runoff? Kasi yun yung baha. Yun yung dinedesign mo. Yun yung more than the infiltration or yung kasi yung infiltration, bababa lang naman yung tubig. So, kailangan mo syempre dyan yung permeability o yung capacity ng soil na mag-infiltrate yung water. Syempre, kung hindi naman niya kaya mag-infiltrate doon, like for example, kung clay yan or cemented yung soil, I mean, sobrang compact. So, hindi masyadong mag-infiltrate yung water. And then, magiging runoff yan. So, or baha. There are 3 methods. And these methods are the constant discharge method, the concave method, and the constant slope method. So, as we can see, dito sa figure na to, baseflow separation methods, pinaplot yung time at saka yung discharge or yung CFS, cubic foot per second, nung 'di ba sa fluid mechanics na or sa hydraulics na pag-aralan niyo yung mga discharge. So, ganoon din sa ulan. So, 'di ba, umuulan, so may discharge. Gaano karami yung ulan? Okay. So, yung discharge, makukuha mo yan by multiplying the precipitation in inches per hour times the area nung watershed or nung lugar na kino-consider mo. Okay, so normally kasi ang graph ng or ang hydrograph, so ito kasi hydrograph yan. So mag-start yung storm at time 0. So ayan, dito na lang nag-start. So bababa yan and then tataas, magkakaroon ng peak and then eventually bababa. Yan. So, ini-smoothen na yung curve. So, ganyan na yan. So, di ba yung parang kanina mga bar-bar. So, ngayon, ini-smoothen na or ginawa ng curve. Mag-start tayo sa constant discharge method. So, paano sineseparate yung base flow at saka yung runoff? So, sa constant discharge method, hahanapin mo lang yung lowest point or T sub S and Q sub S. So, yun yung coordinate, T sub S, Q sub S. Hanapin mo lang yung point na yun and then i-project mo siya horizontally hanggang dito sa dulo, hanggang ma-meet na ito. And then, yung amount of rainfall or yung amount of discharge na nandito sa taas, yun yung direct runoff. And then, yung nasa ibaba, yun yung base flow. So, yung ganun yung pag-analyze ng constant discharge. Paano naman yung dito tayo sa constant slope naman. So, sa constant slope, hindi kino-consider na horizontal yung base flow. Okay? So, hinahanap yung inflection point nung hydrograph or nung curve. So, what is the inflection point? So, from your differential calculus, di ba the inflection point is where the second derivative of the function is equal to 0. Di ba pag first derivative, it is the minimum or maximum point. Like for this example, so ito, first derivative, kung alam mo yung function na to, first derivative niya, hanapin mo lang yung x or yung coordinate or yung abscissa, then i-project mo lang dito para makuha mo yung y coordinate o yung q sub s or the discharge. Pag sa constant slope, kailangan mong hanapin yung inflection point dito sa side na to. So, paano malalaman yung yung inflection point? 'Di ba? Ang inflection point is the change of concavity nung graph. So, kung ito ay concave downward, yan, so pababa siya, 'di ba? Yan, paganyan siya. So, dito naman concave upward na yan, 'di ba? So, parang paganyan na siya. So, hanapin mo lang yung point na kung saan magkakaroon siya ng change in concavity. So, from downward to upward. O yung slope niya, actually hindi slope yung second derivative o yung change in slope, I think, ay 0. And that is this point. So, pangalanan mo siyang Q sub R and T sub R. Yan. So, mamaya, meron tayong na-solve na nila yung function sa pagkuha nung Q sub R and T sub R. Mamaya sa next slides. Pero, graphically, pinapakita ko sa inyo kung paano siya makukuha. Okay, so yung discharge or itong mga nasa taas ng line na ito, from the lowest point hanggang doon sa inflection point, constant slope yan. Then yung nasa taas niyan, yun yung direct runoff. Yung nasa baba, yung base flow. And then the last one is the concave method. Sabihin naka-concave siya or meron siyang minimum point. So, paano makukuha yung minimum point? So, from this line, so mula dito, ang curve kasi ay normally pa ganyan eh. May concavity dito. So i-project mo lang yung straight line papunta dito. Then, i-project mo yung from the peak or the highest point, project mo downward vertically para ma-meet niya yung line na ito. Then, from this point, sa intersection ng dalawang lines, you draw another linear or another line from here hanggang sa inflection point. And then, yan ngayon yung boundary nung base flow at saka nung direct runoff. Okay. So, I hope naintindihan nyo siya. May example naman tayo later. Yung mga formula, na-derive na nila yan. So, gagamitin nyo na lang. Pero, dyan nakuha yung formula, dyan na-derive. Yan. So, ito yung isa pang example. Isa pa palang tag dito. Illustration. So, discharge or flow, time, base flow separation line. Yan. So, gumamit siya ng constant slope. Duration of excess precipitation. So, may excess precipitation dito. Then, ayan, may rising limb and then may recession curve. Ibig sabihin, patapos na or pahina na, pahupa na yung ulan. Okay, so, ayan. So, ito yung mga equations na gagamitin. For constant discharge, okay, so, there are 3 equations from time t hanggang sa t sub s. So, from, I think, siguro, start tayo dito sa t sub o hanggang dito. So, constant discharge. So, ang gagamitin mong Q ay yung Q yung Q o yung discharge dun sa graph. And then, kung may yung Q sub S, yan, so ito yung Q sub S, itong horizontal line, gagamitin mo siya from T sub S hanggang T sub E. ito, hanggang dito. Yan. So, gagamitin mo siya para makuha yung Q sub S. And then, yung Q sub, yung isa pang Q ay from T sub E onwards. Q sub B is the base flow discharge. Okay. Ito naman lang sa constant slope. Para makuha mo yung base flow discharge, Q sub B. So, yung Q sub B from T sub S ay yung Q dun sa graph mismo. And then, para naman dito from T sub S to T sub R, yung Q sub B or yung base flow discharge ay ito. Yan, gagamitin mo tong function na to. Okay, and then from T sub R, so mula dito hanggang doon, yung Q sub B mo is equal to Q o yung nandito mismo o yung coordinates mismo dito. Then ito dito. Ibig sabihin, ito ang base flow discharge mo. Okay, so paano malalaman yung runoff discharge? Pag ma-minusin mo lang yun, ito, i-minus mo doon sa makukuha mong base flow discharge para makuha mo yung discharge runoff. Okay? So, mamaya may table tayo doon. Papakita ko sa inyo. Mas madali kasing kuhanin yung Q sub B o yung base flow discharge. And then, same with the Q sub B. So, halos similar lang nung procedure. Kaya lang, may apat yung apat yung areas mo. So, area 1, area 2, area 3, and area 4. Okay, so kaya apat yan. Yan, so ito yung example. Meron tayong event ng ulan o may ulan. Then may flow rate siya or may discharge. So naka-multiply na siya sa area. So yung precipitation multiplied by the area or the rainfall multiplied by the area. Kaya naka-cubic feet per second na siya or CFS. So, ang interval ng pagkuha ng data is every 30 minutes. So, 9:30, 10 a.m., 10:30, 11, and so on hanggang 4:30 and then 5 o'clock, 5 p.m. So, yan. Medyo matagal-tagal yung ulan. Then, ayan. Makikita nyo, bumugso yung ulan, humina, tapos pataas. And, nag-peak siya sa alas 12. So, 12, 153. Then, nag-recession na siya eventually. Then, ayan, pag ganyan. So, ito yung hydrograph. Ayan. So, Green-Ampt ko lang siya ng ganyan, as is. So, yan. Para makuha, ito, pinakita ko na sa inyo yung, kasi sa book, doon sa libro ni McQueen, wala siyang graph. Pero, ito, Green-Ampt ko na para makita nyo. Yan. So, ito yung sa constant discharge. Ito sa constant discharge. And then, ito sa constant slope. Ito constant discharge. Ito constant slope. Ito sa yung may concave. Yan. So, ito may intersection siya dyan. Ito project mo lang and then ito hanggang sa inflection point. So, ito yung inflection point kasi ito yung concavity niya. Gumanyan siya. And then, bigla na siyang nag-change ng course. Yan. So, medyo pa-concave na siya kung titignan maigi. Pero halos linear siya, di ba? Yan. Pero, yan, nag-change ng slope. Okay, so, ito yung computations gamit yung mga formulas kanina, yung QB or yung discharge, yung pagkuha ng base flow discharge. Okay. So, ang kukuhanin mo kasi is QB. So, para makakuha mo yung direct runoff, pag ma-minusin mo lang yung dalawa. So, sa constant discharge method, kung makikita nyo, di ba ito yung mga data, yung raw data. Yan. So, di ba sa constant discharge method, ilang area ba yun? 3 din, di ba? 3 area. So, 61, 61, 49, same lang, 49, and then 40, 40. So, ito na yung bottom. Diba? And then, tumaas na siya, 54. And then, 40 na to. Diba? Diba, sabi, ipoproject lang yung bottom or yung lowest value. Then, i-discharge horizontally. Kaya, 40 tong base flow discharge. Mula dito, hanggang dito sa, ma-intersect na yung isa pang curve. And then, after nun, yung baseflow discharge ay nandoon na sa kukuhanin mo na yung nasa graph or kakopy mo na lang ito. 36, 29, and 22. So, yan. So, ito yung constant discharge, base flow discharge. And then, pag ma-minusin mo yung dalawa, 61 minus 61 is 0. So, ito yung discharge runoff. And then, yan. So, we have 490 cubic foot per second. For the constant slope method, yan. So, ginamit natin yung QB para sa yung formula kanina, 'di ba? Na pinakita ko, 'yan. And then kinuha natin yung total. So, total discharge natin is or yung base flow discharge is 275. And then for the concave, we have 419. So, ano napansin niyo? Parang maliit yung constant slope, 'di ba? Okay? So, 'yan. Ang tanong, ano yung best? So, yun, depende yun sa situation and depende sa designer. So, kung medyo conservative ka, pwede ka naman mag-constant discharge or piliin mo yung pinakamalaki, yung makukuha mong runoff. Di ba? Kasi wala naman talagang, yung mga, ito kasi, mga model lang to. Or ibig sabihin, mga experimental, tinest lang nila experimentally. So, kung ano yung fit doon sa lugar nyo o doon sa watershed na ina-analyze mo, I think yun yung gamitin mo or doon sa area na dinidesign mo or urban area na dinidesign mo. For example, isang community or land development, isa kang land development engineer. So, yun. Gamitin mo yung mas conservative or yung mas conservative. Yes. Okay, lalo dito sa Philippines. Yan. Ngayon, paano mako-convert yung discharge into yung CFS into rainfall depth. Okay. O yung volume into yan, in terms of inches. Yan, ko-convert mo lang yung yung 490, diba ito yung sa constant discharge, cubic feet per second. Yan, and then kinonvert lang yan dun sa number of 30 minutes siya. Then, ayan, cancel. Okay. And then, ito, conversion factor, 12 inches per feet. Okay. I think yung 74 acres ay yung area ng lugar. Okay. Yan. So, between 10:30 to 15:30. Okay. Okay, so then ito yung isa pa para naman sa for the constant slope method, the following equation defines base flow for the period from the storm time 10:30 to the recession inflection point at 13:30. Okay. Okay, the resulting base flow is given in column 5. Okay. Then, ito naman yung sa concave. And then, the resulting is 2.1. The computed base flows are given in column 7. The computed volume of direct runoff is 2.81. So, ibig sabihin, 2.81 yung baha na may experience dun sa area na yon. Okay. 2.81, di ba? Parang ano lang yan? Parang hanggang sakong lang, di ba? Okay, so what more pa kaya kung sa Philippines, so mga baka 5 feet yung makompute natin. Try nga natin. Gamitin natin yung gawin nating ano ba yung mga lugar na Marikina. Gamitin nating watershed yung Marikina. Anyway, Master-depletion curve. So that's all for base flow and base flow separation. Okay. So Master-depletion curve naman, ito ay ginagamit sa mga projection. Okay. So model din ito. The Master-depletion curve method is used to provide a model of flow from groundwater storage. Based on this, it can be used to identify a point on the recession where direct runoff ends and base flow begins. Okay, however, it also provides a model of the recession limb. The procedure requires measured storm hydrographs for a good number of storm events covering a wide range of volumes and for different seasons of the year. Yan. So, gumagamit siya ng past data ng mga storm. Okay. Yan. So, ito yung method. So, number 1, using semi-log paper, log Q versus time. Plot the recession curves. So, ibig sabihin ng recession, yung patapos na. Okay, yung pahupa na yung ulan. So, yun lang ang ipa-plot mo. Kung meron kang mga rainfall hydrographs, kukuhanin mo lang yung recession curves for each storm event on separate piece of tracing paper. Yan. So, yan, graph mo lang siya on a master sheet having a log Q versus time axis. So, meron kang isa pang master sheet or meron ka pang isang semi-log paper. Plot the recession for the storm event having the smallest values of log Q. And then, using the recession curve with the next smallest value. So, mag-start kayo sa smallest value ng recession curve. Okay, so may mga recession curve kasi na value na matataas at may mabababa. And then, pag susunod-sunodin mo lang siya mula sa mababa and then pataas, ipa-plot mo siya ng sunod-sunod dun sa isa pang tracing paper na ginawa mo. Yan. And then, i-arrange mo lang siya such that the curve appears to extend along a line coincident with the recession of the first event plotted. So, dapat makita mo yung trend ng mga recession curves. Continue this process using successively larger magnitude log Q recessions until all storm events are plotted. So, kung meron kang 5 storm events na may mga recession curves, ipa-plot mo siya isa-isa dun sa tracing paper para hanggang sa makakuha ka ng isang line. Then, yung line na yun yung tinatawag na Master-depletion curve. Yan. So, yan. So, ito yung equation ng Master-depletion curve. Okay, so, yan. Ito ay dinerive na lang para makuha yung value ng K. And then, ito, ayan, para ma-solve din yung K. Kasi yung K is parameter, important parameter siya. Okay. Actually, yun yung makukuha, yun yung kailangan mo para, yung parang slope siya nung curve. Pero sa Excel, madali lang gawin to. Madaling makuha yung equation na yan. Okay. Pag nakuha mo na yung value ng K kasi, pagka meron kang another storm event, kaya mong i-project yung Baseflow, yung recession niya. Okay. So, let's have some example. Okay. So, meron tayong storm event, 1, 2, 3, 4, 5. So, yan yung mga actual storm event na nangyari. And then, ito, test event. Sabihin yung test event, test lang natin yung magagawa nating model or equation or yung master depletion curve na makukuha natin, itetest natin kung gagana siya dito sa test event. Okay. Pero ito lang yung gagamitin natin para ma-formulate yung equation ng master depletion curve. So, yan. So, ito yung 5 recession curve. So, yan. Mga recession curve lang siya. Sabihin yung patapos na. So, technically, dapat ganyan yan. So, ito lang yung kinuha natin. Okay. So, yan. Ipa-plot natin tong 5 na to sa isang tracing paper. So, sabi, mag-start ka daw sa pinakamababa. So, ito yon. Diba? Ito yung pinakamababa, yung Q. Then, sunod to, and then ito. So, ito, pa-plot mo siya. For example, yan yung plot niyan. Then, yung pangalawa. Yan. Then, yung pangatlo. Ipa-plot mo siyang paganyan ng paganyan. Diba? Then, ito yung tinatawag na line. Yan. Yan. So, diba? Ito yung pinakamababa. So, ito yun. Then, April 1937, 1941. So, tingnan nyo, iba-iba siya ng petsa. Okay? Then, yung line na yan, ito yung tinatawag na master depletion curve. Okay? Para makuha mo yung slope ng curve na to, and then yung equation ng curve na yan, you can use Excel or you can use the formula given. Okay? Yung binigay kanina. Yan. Or mag-rise overrun ka na lang dyan. Diba? So, makukuha mo kasi yung point na to, and then yung point of intersection here. And then yung time corresponding, and then yung time. Itong time na to, I think, parang 0 to 540, parang standard na ginamit ni McQueen or nung nag-develop nito. Kaya, yun din yung ginamit ko sa ibang example eh. Okay, so I don't know bakit hanggang 540 yung ginamit nila. Or bakit hindi na lang 0 hanggang 120 or 180. Okay? Yan. So ito, ang nakuha niyang value ng K is 0.0041 and then the master depletion curve equation or function is ito, discharge, tsaka meron kang time. Okay, so para magamit mo yung data na to, the data for the test event of table 9-2 can be used to show how the master depletion curve can be used to define the end of the direct runoff. Okay, so plotting the logarithms of the data on tracing paper and superimposing the resulting recession onto the master depletion curve of figure 9-4 indicates that the direct runoff ends at a discharge of 8 cubic foot per second. Thus, the baseflow can be separated from the direct runoff by connecting a line from the discharge at the time t is equal to 0 to the discharge of 8 cubic foot per second. Okay. So, paano nalaman yung 8 cubic foot per second? So, diba ito yung test event? So, kailangan hanapin mo lang itong value na to. So, I think nasa pagitan siya nitong dalawang recession curves na ito. Yung 411 and 323. So, ito yon, itong dalawa. So, itong test event natin, ipa-plot mo siya somewhere here. Ayan, so somewhere dyan, di ba? Tama ba? And then, kung ipa-project mo to, ayan, 8. Tama ba? Yan. Yan. So, almost nasa 8 siya. Yan. So, in-estimate na lang natin na 8 CFS or cubic foot per second yung discharge. Okay. Doon sa storm event na yan. Okay. Yan. So, yun. Then, punta naman tayo sa separation of losses using index methods. Okay, so the first one is the Phi Index Method. So by definition, the Phi Index equals the average rainfall intensity or depth above which the volume of rainfall excess equals the volume of direct runoff. Thus, the value of parang kulang siya, is suggested such that the volume of rainfall excess and direct runoff are equal. So the procedure for computing the Phi Index is listed here. So compute the depths of rainfall B sub P and the direct runoff V sub D. Okay, so depth. Make an initial estimate of the Phi Index. So gagamitin natin yung formula na to. Okay, Phi is equal to V sub P minus V sub D, in which D is the duration of rainfall. Excluding that part separated as initial abstraction. So, yung initial abstraction parang yung pauna or yung unang bugso, parang ganun. So, parang hindi siya kailangang isama. And then, the Phi is an intensity with dimension of length per unit time, such as inches per hour. And then, compute the loss function. Okay. So, S of T is, ayan. So, Phi, if P is less than or equal to the P of T. P of T is the ordinate of the rainfall intensity hyetograph at time T. So, kung meron kang hyetograph, yung mga bar graph na ganyan-ganyan. So, yun yung hyetograph. Yan. So, yun yung rainfall intensity, P sub T. Then, P sub T if Phi is greater than P sub T. So, yun yung loss function. And then, compute the total depth of losses. Okay, so ang depth ng loss is the summation of S sub T multiplied by delta T. Compute E sub of T is equal to P sub T minus L sub T for all ordinates in the rainfall hyetograph excluding initial abstraction. And then, number 5, compare V sub L and V sub P minus V sub D. Okay, and then, yan. Use the latest, use the latest Phi to define losses. Actually, ang hirap basahin. Pero, yan, i-explain na lang natin siya sa isang example. Okay, so ito yung example. Consider the rainfall hyetograph of figure 9-7A. Yan. So, bakit ba may tinatawag na losses? Meron kasi yung, ibig sabihin ng loss, yun yung yun yung mga rainfall na, bawa, nag-evaporate. Yung sinabi ko nga sa inyo, nag-evaporate agad, or kung saan napunta, or na ano sa halaman, sinipsip ng halaman, or what. So, yun yung mga losses. So, yun yung tinatanggal siya sa pag-compute ng ano. Yun, kaya tinatawag separation of losses sa pag-compute ng mga rainfall excess. So, yung rainfall excess, di ba, yun yung mga nagiging flood eh. Okay. So, consider the rainfall hyetograph assuming that the depth of runoff is 0.4. Okay. The value of phi must be set such that the depth of the rainfall excess equals 0.4 inches or 4.4 inch. Therefore, rainfall losses would equal to 0.3. The value of phi is computed with equation 9-9. Okay. 0.7 minus 0.4. I think isa dito ay 0.7. And then isa ay 0.4. Okay, so okay, 0.7 minus 0.4 all over 4 hours. 0.3 inch over 4 hours, 0.0725 inches or inch per hour. Subtracting a loss of 0.075 inch per hour from each ordinate of the hyetograph yields a time distribution of rainfall excess. Yan. So, yung hyetograph, babawas mo yung losses na to. Then, magkakaroon ka ng mga bagong ordinates or rainfall. So, yan. Converting this to depths and summing yields a total of 0.4 inch, which equals the volume of direct runoff. Thus, the computed value of phi is appropriate for this storm event. So, yun. Hahanapin mo lang yung value ng phi. And then, constant percentage method. So, the constant percentage method assumes that losses are proportional to the rainfall intensity. Letting f the fraction of rainfall that contributes to losses, then assuming that depth of rainfall excess P equals the depth of direct runoff Q sub D. The value is given by the value of F, in which P is the total depth of rainfall. Okay. So, yung F ay yung so, 1 minus 0.4 over 0.7 is equal to 0.4286. Multiplying each ordinate by the rainfall hyetograph by F yields the loss function. So, thus the loss function for the rainfall of figure 9-7A would be 0.043 and then so on. And the distribution of rainfall excess would be, okay, parang mali yung nalagay kong mali yung nalagay kong figure. Pero, yan, check nyo na lang dun sa book. Yan, so ito yung F, i-multiply mo lang siya dun sa, ito yung loss function, i-multiply mo siya dun sa ordinates. Then, i-minus mo siya dun sa ordinates. Okay. This method does not require an iterative procedure. Okay, so yun yung Phi Index, yun yung index method sa pag-compute ng separation of losses. Yan, so another method ay yung infiltration capacity curve. So yung infiltration o yung pag-penetrate ng water sa soil is another type of loss, 'di ba? Okay, so from kanina, 'di ba, yung mayroon tayong computation ng Baseflow, 'di ba sabi ko sa inyo maraming models na ginagamit ng mga hydrologists. And meron na tayong Baseflow separation, meron na tayong index method sa pag-compute ng loss. And then another one is the infiltration capacity curve. So dalawa to, yung isa Horton, yung isa Green-Ampt. Okay, so nahin natin yung Hortons. infiltration capacity curve. So, medyo marami-rami mga equations dito eh. So, yan. Pagka medyo hindi kayo naiintindihan sa mga dinidiscuss ko, tanongin nyo na lang ako or i-PM nyo ako. Kasi medyo masakit yung lalamunan ko. Okay. Okay, so sabi ni Horton, yung infiltration capacity o yung capacity ng soil na mag-infiltrate dun sa isang lugar, sa isang watershed, is equal to F is equal to F sub C plus the difference between F sub O and F sub C multiplied by e raised to the negative KT, where T is the time, in which F sub C is the infiltration capacity after a long period of continued wetting, F is the initial capacity, and then that's the capacity of the beginning of a storm event that occurs after a dry period. T is the time from the beginning of rainfall, and K is a constant that describes the decay of the capacity with time and reflects the soil cover complex. Given estimates of FO, FC, and K, the infiltration capacity curve can be computed for the duration of a storm event and used to separate losses and rainfall excess. Okay. Ito isang example. Yan. So, binigay na yung value ni FO, FC, and then K. So, ito na yung infiltration capacity curve ni Horton. Yan. So, paano mo solve yung... So, ang goal natin dito ay ma-separate yung loss at yung excess. Okay. So, ito yung F. So, ito given time and then yung precipitation or yung rainfall. Solve mo lang yung F. So, ito, na-solve na niya. Okay, gagamitin mo ito for every time t. And then, change in F. Ano ba itong change in F? I think i-multiply mo to sa time. So, 0 multiplied by 0.6 is 0. 0.25 multiplied by 0.544 is this one, and so on. And then, yung P sub E is the excess. So, I think pag ma-minusin mo itong dalawa, 0.7 minus 0.6, and then 0.7 minus 0.544, and so on. And then, yung F, ano tong F? Inches. Cumulative. Okay. So, 0 plus 0.143. Ito, 0.143 times 0.3. Ito, and so on. Okay, so basahin natin to. The infiltration capacity F was computed for the period of storm times from 0 to 4 hour. So, using the trapezoidal rule, the depth of infiltration for each increment of 0.25 hour is also given in table 9-4. The total depth of infiltration for 4 hour was 1.407 K, which yields a rainfall excess of 0.693 inches or inch. Integration of equation 9-15 yields a total depth of infiltration of 1.406. Okay, so dito kasi ang na-compute natin using trapezoidal rule. So, ano yan, hinati-hati into trapezoids. Diba saan ba ano yan? Sa highway engineering, ginagamit din yan. And saan pa ba ginagamit yung trapezoidal rule? Sa calculus. Okay. Pero pwede ka rin gumamit ng integration. Sa mga calculator nyo, may integration dyan. So, pwede nyo i-integrate ito. Yan, ito, yan. Ang lagay nyo lang, i-type nyo to, yung t palitan nyo ng x. Ito, ilagay nyo from 0 to, yan, 4 hours. And then, makukuha mo ay ito, 1.406. Which indicates that the trapezoidal rule provide an estimate within. Yan. So, actually, pares lang. Yung kasi yung integration, doon lang din naman nakuha yun sa trapezoidal rule. Okay. Parang, ano lang. Ayun. Hindi ko alam kung bakit ginawa pa niya parehas. So, dapat isa na lang. Dapat din na siya nag-integrate. Siguro pan-check. Okay. So, yan. So, meron ka ng, so, nakuha mo na yung excess at saka yung total depth infiltrated or yung nag-infiltrate na water. Okay, so meron pang ibang method dun sa Horton, yung recovery and then yung ano pa isa? Basta meron pang isa eh. Hindi na natin siya i-discuss kasi minodify niya lang naman yung yung Horton's infiltration capacity curve. So, dito naman tayo sa mass infiltration method. So, in the example of figure 9-8, the rainfall intensity was always greater than infiltration capacity. So, kagaya nung kanina, ibig sabihin, mas malakas yung rainfall kaysa doon sa capacity nung water. So, ibig sabihin, nag-expect talaga tayo ng runoff, di ba, or ng excess. When such a condition exists, the available water is sufficient such that the rate of infiltration equals the capacity of the soil structure to store and transmit the water. In cases where the rainfall intensity is less than the infiltration capacity, all of the available soil storage is not used. Ibig sabihin, lahat ng soil mag-i-infiltrate lang. Thus, the capacity does not decrease at the same rate as it would if the rainfall intensity were equal to or greater than the capacity. If one assumes that the capacity decreases at the rate given by equation 9-14 o yung kanina, yung Hortons, when it would actually be less than the capacity, the volume of losses will be underestimated and the volume of rainfall excess will be overestimated. Okay, so the mass infiltration method can be used. Yun, gaya nga nun, kapag hindi naman sobrang dami nung ulan at mas marami naman yung infiltration capacity, so ito ang gagamitin mo. Itong mass infiltration method. And then, yan. So, yan yung formula. Total mass infiltrated water. Ayan. So, wala tong excess unless, yan. Kagaya nito, dito sa part na to, okay, a plot of F given by 9-20b versus F is called the mass infiltration curve. So, ito yung 9-20. Wala pala dito. Using the mass infiltration curve, the infiltration capacity can be computed for any value of F. When the rainfall intensity is less than the infiltration capacity, the volume of infiltration F, which is assumed to be equal to the total volume of rainfall up to the specific time t, can be computed and the infiltration capacity determined. Okay, so dito sa graph na to, ito yung infiltration curve. Ito yung infiltration. And then, ito naman yung hydrograph mo o yung rainfall. So, ibig sabihin, yung capacity niya mas mataas. Di ba? Kumpara dun sa rainfall o dun sa so, walang excess. Until such time na mag-intersect silang dalawa. So, dito sa part na to, ito na yung excess. Ito na yung excess rainfall. Okay, and then, pag Green-Ampt mo yung infiltration rate at saka mass infiltration volume, ganito siya. So, ano ibig sabihin nun? Ibig sabihin nun, habang habang tumataas yung volume, ano ba to? Habang mass infiltration rate. So, ayan. So, di ba may infiltration rate? Okay. So, pagka yung volume ay mass infiltration volume. So, habang dumadami yung volume na nag-i-infiltrate, bumababa yung infiltration rate. Okay. So, habang dumadami nag-i-infiltrate, bumababa yung infiltration rate. Kasi na-occupy na nila yung soil. Okay, so yun. Analysis and synthesis, an approximate infiltration capacity curve can be drawn if values are available for 2 of the 3 coefficients of equation 9-14. So, yung 9-14 yung Horton. So, the ultimate capacity F sub C and the decay coefficient K are probably easier to relate to the soil and cover characteristics. So, values for these variables may be available. If the depth of losses is known, F can be used to represent the depth of losses, and equation 9-20b can be solved for F sub O. Yan. In equation 9-20, the duration of the storm event and F sub O is the initial infiltration capacity. So, F sub O is the initial infiltration capacity. Yan. So, ito yung example ng analysis and synthesis. Figure 9-12 shows a 4-hour rainfall hyetograph. So, yan. So, may ulan. And then, if you assume that analysis of the runoff hydrograph resulted in a depth of direct runoff of 1.1, there would be 1.1 inch of rainfall excess. So, since the total depth of rainfall is 1.8, okay, so pag sinum up to ay 1.8, the infiltration capacity curve must separate 0.7 inches of loss. Okay, and if soil studies suggest that KFC equation, and then ayan. So, ito yung infiltration capacity function. And then, ang nakuhang infiltration capacity curve is 0.457 inch per hour. Based on this value of the infiltration capacity curve of 9-12A was drawn. Okay. So, ito yung infiltration capacity curve, and then ito yung loss, and then sa baba niya is yung rainfall excess. Okay, so nasan dyan yung 0.457. I think ito yung 0.457 somewhere here. Then tsaka siya hanggang doon. At time is equal to 4, or sa katapusan, ang magiging ordinate is around 0.1. Okay? Okay, so yun yung para sa infiltration capacity using Horton's model. Para naman sa Green-Ampt model. So, the Green-Ampt model is a conceptual representation of the infiltration process. So, developed by Green and Ampt, and then it follows the Darcy's law. Okay, so kanina meron kang hindi ginagamit yung diba, yung coefficient of permeability. So, dun sa Horton. So, meron lang siyang soil factor na K. Pero dito, ginamit yung Darcy's law. Kasi diba yun yung nag-govern sa permeability ng soil. Yan. So, kailangan mo lang dito is the moisture content ng soil. Itong theta sub S and theta sub I. Okay? Saturated tsaka initial. Okay, so yun yung ibig sabihin ng dalawa. And then, L is length. Yan, and then, pinagsama yung dalawa. Then, yan, meron ka ng infiltration capacity curve na F sub, yan, meron kang K. Yung S sub W, ano nga ba to? Later sa example. So, in applying equations 934 and 935, the underlying assumptions should be recognized. So, as rain continues to fall and water infiltrates, the wetting front advances at the same rate through the groundwater system, which produces a well-defined wetting front. So, the volumetric water contents, water contents, remain constant above and below the wetting front as it advances. So, the soil water suction immediately below the wetting front remains constant with both time and allocation as the wetting front advances. Okay. So, if the rainfall has constant intensity I and exceeds the infiltration capacity F, the infiltration rate will equal the intensity I until ponding occurs. So, syempre, at that time, accumulative depth F sub P will have infiltrated, which can be estimated from equation 9-35. Okay, and then ito may modification na ginawa in which T sub E is the equivalent time to infiltrate a depth F sub P when subject to initially ponded surface conditions. Yan. May konting modification lang na ginawa. And then, yan. So, yan. Let's try an example na lang. In the synthesis mode, input values are required for KS, SW, I think property ng soil. Yan, so hindi ko na nakalimutan ko eh. So yan, sa book naman ito, saka sa module. And then theta sub I, mga moisture content, as well as the rainfall intensity I. So the following values are assumed as inputs. So yan. And then the soil water deficit at the beginning of rainfall is given 0.3. And then solving equation 9-36 for the depth of infiltration at time of ponding. Yan, depth of infiltration at time of ponding pala yung F sub P. Then ito yung formula niya. And then substitute lang natin yung mga parameters. Yan, so ito yung depth of infiltration at the time of ponding. So 158. At the time of ponding, the infiltration capacity equals the rainfall intensity. So, di ba, 158 for a constant rainfall intensity from the beginning of rainfall to the time at which ponding begins. The depth of infiltration is F sub P multiplied by I is equal to I multiplied by T sub P. So, yung depth of infiltration at the time of ponding, yung I ay yung intensity, and then yung T is time. Kung kailan nag-start yung ponding. And then, so you can compute for the time kung kailan nag-start yung ponding, which is 0.395 hour. The cumulative depth of infiltration F and the infiltration rate F, small letter f, can be determined from equations respectively. Okay, so yan. Puro direct substitution lang naman to eh. Okay, so equation 9-37 requires the equivalent time T sub E that would have been required to infiltrate the depth F sub P. This can be estimated by rearranging equation 9-37 to compute T, which is T sub E. Yan, so meron na tayong T sub E. Okay, so equivalent time. Then pag nakuha mo na yung equivalent time na 0.20 hour, so now equation 9-37 can be used to define the cumulative depth of infiltration. Okay, so since F appears non-linearly, then a plot of F versus T can be used to estimate either F for any value of T or T for any value of F. So, palitan sila. So, meron ka ng T sub P, na-compute mo na yan. T sub E, ito yon. Then yung F, K sub S. Actually, function siya eh. Function siya nung depth. Diba? Kasi yung mga iba na to ay mga constant. Yung F ay yung depth ng or cumulative depth of infiltration. Okay, so cumulative computation of infiltration rate F and times T at which cumulative infiltration volume equals F using Green-Ampt model. So, ayan, ito yung mga time natin in hours. So, time 0, the 0 depth. 0.395 yung time. And then, ito yung 0.158. Ang pwede kasing gawin dito ay mag-assume ka ng values eh. Or mag-assume ka ng value ng F. And then, kasi diba yung equation na nakuha mo, yung Green-Ampt model na nakuha mo ay for F and T eh. So, pag naglagay ka ng value ng F, mako-compute mo yung T and vice versa. Okay? So, ang kailangan mong malaman is the volume of infiltration after some time. Bawa, after 2 hours. So, after 2 hours, ang volume of infiltration mo or depth of infiltration is around 0.5 inch. Okay? So, ganun yun. And you can also, yan. Yung F naman, pag di-divide mo lang yung dalawa, di ba? Inches per hour. So, kaya mag-graph mo itong curve na to. Okay? Okay, so, yan. So, ibig sabihin, so sa umpisa ng ulan, so mataas yung rainfall capacity niya. So, unti-unti siyang, bababa. Okay? So, parang asymptotic to or halos baka na siya sa 0, di ba? Pag graph yung function. Sabihin, ito ay boundary. Lahat ng lalampas dito sa values na ito ay excess na or rainfall excess. Okay? And then lahat ng nasa baba niya ay losses or infiltration. Okay, so ganun yun. Yun yung ibig sabihin ng Green-Ampt model. Madali lang actually siya. Kasi puro direct substitution siya. Medyo nahirapan lang ako mag-explain sa dami ng mga parameters din na kailangan. So, yun din kasi yung tinitingnan sa pagsosolve ng mga sa paggamit ng mga models. Okay? So, may mga parameters kasi pwedeng yung iba dyan ay kailangan pang mag-conduct ng experiment para magamit mo. Like, for example, permeability ng soil. And we all know na lalo pag clay, mahirap or matagal kuhanin ang coefficient of permeability. And also, soil is highly uncertain. So, pwedeng dito may clay or sa isang side or sa kabilang side ng watershed mo ay hindi naman clay yung soil. So, sabihin, marami kang types of soil. Okay. Yan. So, at ayan, nakasang oras na pala tayo. So, yun. Yun yung part 1, part 2 ng ating hydrology. So, we have discussed sa part 1, 'di ba, yung precipitation, yung descent polygon, yung isohyatal, and then yung pag-compute ng missing data. And then sa part 2 ay all about losses, infiltration, and baseflow and runoff. Okay. So sa midterm natin, ang aralin naman natin ay evaporation. Okay. And then sa finals or sa final term ay unit hydrographs. So parang babalikan natin tong hydrographs na ito pero unit hydrographs na siya. Or may mga models din doon na pwedeng magamit. Okay. So sa pag-compute pa rin ng mga runoff siya magagamit. Okay, thank you for listening. If you have question, PM nyo na lang ako or comment kayo kahit saan channel. Okay, thank you.